Alright, you guys. I hope you guys are using this break and however you want to use it. I'm going to go over exam 1 today. I know that we have the quiz next Wednesday. Remember that I'll be in the media center and available for you guys to come ask questions. You know, it's free to text me. This is your key. So the first one says the kid kicks a ball at the angle of 40 degrees. Sorry, this computer's a little slower. Okay. So then you have your initial diagram, right? You kick the ball over here. And then whenever it says angle, you're assuming it's with the horizontal. Oops, sorry. 40 degrees. With an initial velocity of 8 meters per second. Right? Still V naught. So then ask for the maximum height. And you actually can't find the maximum height yet, because right, your kinematics equations, you have actually it'll probably be y in our case. Y is equal to y naught plus by naught t plus 1 over 2at squared. Right, theoretically, you could use this one to solve for your like y maximum when you're when you're at the top. So remember at the top here, you have v is equal to 0 meters per second, because it has to slow down and stop before it can start coming back down. And then this is also your max height. Right, because if you're going up and then you stop going up and start going down, that's the highest you're ever going to go. And then we have our v is equal to v plus at. This one we have v, that's here. We have v naught, that's here. And we have a, which is gravity, right? Because we're doing positive directions here and here. So that means that negative gravity. So then we're going to use this one where v max, no, not v max, I'm not sure how you would label that. It will be up to preference. You could do v top. I'm just gonna leave it as v equal to v naught is equal to, sorry, meters over seconds. We're defining everything first. V naught go to, well, 8 meters per second, but remember we're on the y-axis. So if we were here, you still have a vx here, and this is vy, right? Because there's no acceleration in the x direction, your velocity on the x-axis is the same for all of the equations. So we're gonna need to do a little trigonometry here. So there v naught, there v naught x, and then this is our v. Oh, that's not straight. And this is our v naught y. Right, where this is your angle, 40 degrees. This is opposite, so sine. Probably to equal v naught sine theta. Remember we got that because sine is equal to opposite over adjacent, hypotenuse, sorry, opposite over hypotenuse. Multiply the hypotenuse over, so the opposite is equal to sine times the hypotenuse. And here the v naught y is your opposite and the v naught is your hypotenuse. So You probably do that in different color. I'm gonna just write opposite out because I know that it kind of looks like a 0. And that means that this one's cosine. So B naught cosine. Right, so then if we go back to where we're trying to find the time for the equation, we have V naught is equal to 8 meters per second times sine 40 degrees. There's no way right back. What is it? That's V naught sine theta. And then you also know your acceleration. No, this one. Which is negative gravity, which is negative 9.8 meters per second squared. We're solving for t. And I'm going to go ahead and type the next part. So then that means that 0 meters per second is equal to 8 meters per second sine 40 degrees plus yeah, you can definitely solve it out with numbers like this. Yeah, we'll solve it out with numbers. 1.8. That's meters per second squared. T. And then that means you move the 9.8 over. I'll leave space so I can drop arrows. Nope, leave it in green. The drawing should be. So right, we took this side, we move it over. And from here, we're gonna divide by this 9.8 meters per second. And that should give you your seconds. Which I got 0.525-ish. Yeah. So what did you get? All right, alternatively, you could also solve it symbolically. So symbolically, it would be V is equal to V naught plus 8t. Move V naught over, so that's going to be V minus V naught. Or you could have moved, yeah. Symbolically, this probably would have been the best choice. Then you're going to divide by A. T. And that'll give you the same answer because it's going to be 0 minus your negative V naught that's going to become negative over negative, which is positive. Okay. So now that we know, so t equal to 0.525 seconds. Now we can solve for the max height. So that's going to be your y when your v naught is 0 using this time. Oh, we should probably put this in here, huh? So then remember that because over here is t is equal to 0, then it takes you 0 to this number to get up here. So then it takes you the same amount of time to get back down. So that means your total time here, not that we need it yet, but I think that's B. Total time there should be 1.05. 0. And the reason for that is it takes the same amount of time to go up as it does to come down. So that means that T final, we'll do T top here. Equals 2 times T top. Oh. Anyway, back to our problem. Your y naught is 0, right? No, meters per second. Your v naught y we solved for earlier. Well, I can probably put this in actually. Type y 0 meters, 8 meters per second, cosine 40, plus negative 9.8 divided by 2 meters over second squared. And then you're gonna multiply t twice. Oh, I forgot to multiply t here. 0.5 seconds. 0.525 seconds. This little caret symbol is to the power of 2, so squared. So then all that, when you plug it in, should give you y top is equal to 1.35 meters, approximately. All right, now we can double check with the key, which is like right here. So let's see, time check. We didn't solve for why not like this. We just plugged this straight in. So it's the whole unrounded version. But I'm sure if you plug it in, it's the same. And then y is like 1.3. She rounded a little differently with time, so it's expected that ours is a little different. She won't knock off points or something like that. Okay. So then that's A. This is A. Okay. And then how far from where it started does the ball hit the ground? That one, you're going to use the same kinematics equation, this one. But instead of y's, you're going to use x's. I don't think I have the room for that. Yeah, I think I took up too much room with all this stuff. All right. We'll just do D for now. And then I'll like take a screenshot of all this and then go through sleep. So this one, D is asking for the velocity vectors and acceleration vectors at the beginning, max height, and at the ball hits the ground. So you can have a diagram like this. For the beginning, you have your V naught here. You also have your V naught X here. And your V naught Y here. Usually for these, we use the tail to tip method, where like this one goes this way, and then from there, that point of the arrow, the tail of the next one comes up to meet the tip of the resultant vector, in this case, the V naught. Same thing for this one here. You have your V naught X here. And that's basically it, because you don't have a V naught Y. And then here, remember, because it's symmetrical, you have a negative V naught. And then your your components are gonna kind of mimic that. You're gonna have a negative V naught X. And actually it's gonna be positive. Sorry. It's the same direction, but a negative V naught Y. Okay. And then it asks for the acceleration. Yeah, and that one's gonna be here. The acceleration of the Earth. I'm guessing it's just saying gravity. That's why I always took that one. So just remember that gravity is constant throughout the problem. If you want to be technical, all these lines would be like the same amount, like the same length. But yeah. All right. I guess we could write in Vmax up here just so we can, just in case we need it. Nope. Wow. So 1, 1. Okay. I'm gonna go ahead and erase a lot of this stuff. Okay. From here, you're gonna use your x is equal to x naught plus v x naught t plus 1/2 at squared. And remember that acceleration is 0 on the x direction. That's 0. Your x naught is also 0. I should probably write units, meters. Your Vx naught is V naught cosine. Naught. And then your time is your 2 times t top. The t final is equal to 1.05 seconds. Cool. And then this thing we're solving for. Note that you could also do it this way. You could do could probably use this equation to get you BT. But seeing as sometimes we do have an acceleration, then it's usually better just to use the kinematics equation. Because remember, you kind of derived that from this. No, you derived it from this one, but the same kind of idea. This is assuming there's no acceleration. Anyway, so then we have x is equal to v not x t. I'll do right, so we know that's all one thing. Which is equal to v naught cosine theta. I don't really have a theta symbol, so I'm just gonna leave it at that, times t. So then we plug that in. X is equal to 8 meters over seconds. Cosine 40 degrees times time 1.05 seconds, which should give you 6.4 meters. Cool. Go ahead and check that. Yeah, she got 6.42. Her time's a little different here because we had rounded it differently. So then I'll just circle. So then that's this part here. Cool. And then go ahead and clear these. Oh yeah, those are the diagrams that she had of the velocities. Okay. And from here you have to draw the resultants of these two vectors. You probably leave like that. Let's do the others in. Okay. Remember that the resultant of A minus B, this minus here says that the B is going in the opposite direction. Right? So if you see in here, you have your A and then you have your B going the opposite direction. So if you had, okay, just a little bit more. Well, then this is your minus B. And then from there, you can use the parallelogram method, which I'll do in blue, where you kind of go, okay, well, this is the parallel B. And then this here is a parallel A. So then this is a resultant going from this start of both of them. It's the end of both of them. Cool. Then the other one is a tilt tip, which I will do. Let's do it in brown. Tilt tip. So that one I usually draw on its own. We have, I like to just add the angles. Degrees. Right, this is A. And then you have B, which would normally go out this way, 60 degrees, right? But it's going down that way instead. So note that this angle is the same as this angle. So if you were to draw like a horizontal line, then B would be coming down 60 degrees here. Right, because alternatively, if you had A plus B, then you would have, I know my lines aren't straight or anything, but have A 55 degrees, not 58, 55. And then you would have your straight line here. And you'd be coming this way at 60 degrees. And then it's always hard to explain the angles, but like if you have a line coming this way, right? So this is your plus B. This is your minus B. You have 60 degrees here. Then it's like 60 plus 80 to get this whole part. And then if you do that 80, let me just write it. So then this is going to be 180 minus 60 degrees, right? And then if you were to do this part, it would be 180 equal to this is theta plus 180 minus 60. And then if you would like subtract these two, then that means that 0 equals to theta minus 60. So that's a 0, not a theta. So then that means that this angle here sorry, I probably should have labeled that one as theta instead of the other one. That means that this angle is 60 degrees also. If you remember from math or geometry, that's also the same as the parallel line theorem or something like that, where these two are the same. But I know sometimes I really suck at remembering that sort of stuff. Anyway, so then you have the 60 degrees here, and you draw your negative b here. And then that means that your resultant vector would go from here down to here. But you would draw it with the grid and then scale, and then that gives you your two methods. I think you also have to add them like actually using the values, so we'll do that in a little bit. Or maybe on the side over here. Just make sure the drawings are fine. Jesse, that's the parallelogram method that we did here. I mean, if you probably put it, it's probably gonna line up kind of the same. Yeah, about I did the B a little weird. And then that's the tail to tip method that we did here. She didn't actually include angles because it's just the idea of it. Okay. And then it asks, why have we learned about vectors? Give examples. Vectors are really useful because they have magnitude and direction. They show velocity, acceleration, and forces. Sometimes I think displacement counts too. So they're kind of important for explaining the natural world. So I'll write that in later. Let's do, we'll say this is B. So this side is B. And this side is A. You just draw a smaller arrow. I feel like we're gonna need more side play. You have A. 7 meters. You have your AY. This is on the opposite of your theta. So that means that is equal to A sine. Oh, right. This one would probably be better to draw the other way. Same idea. You have your A, but instead of using you go that way, you do it this way. And this is your AY. This is your theta. AX. And then your A, which we know is 7 meters. And you know that your theta is 55 degrees. So then your AY being on the adjacent side is going to be A cosine theta. And your AX being on the opposite side is going to be A sine theta. And then you're going to do the same thing for B, right? This is your positive B. This is your negative B. You don't add a negative sign to this yet. You just know that this side is positive, this side is positive. So then that means that this is positive 2. So it goes up. So see, I like to assign the positive signs to your vectors instead of doing the whole from this line that she does. I'm just gonna make this be. Right, and now see how this one's going down against our negative, so this one's negative BY, and this one is still in the positive direction, so it's still positive. Right, this one's going up, this one's going this way. Seeing as this is on the opposite side, because right, you had your theta here. I'll use psi for this one. And that means that, oh, sorry, it's habit to draw stuff like this. But it really is better to just draw it the way that's easiest in terms of the angles. Same concept though. You still have a positive beta bx, which seeing as this is now your angle, which is the same as that one over there. Then that one's your b cosine. So your negative by, positive, which is your negative b sine theta. Sorry, psi. Sine psi. That's just so that we have different symbols for each angle. Okay, so then we can go ahead and do sigma x and sigma y. I'm gonna type these. Sigma x is equal to ax plus bx. Seeing as they're both positive, that still stands true. So then that's gonna be a sine. I use these two to the theta. Plus b, x for b is cosine. And I'll probably use these to do this side. And we might as well plug it in while we're here. A is 7 meters. Sine of 55 degrees. B is 5 meters. Cosine of 60 degrees. And that should be... Sorry, Buster. My calculator saying 8.23 meters. Then we do the same thing for y. Y is equal to ay plus by. But this time, your by is negative, so you have ay. Oh, I'll just do it here. Negative by. So then you're gonna have your y should be cosine, yeah. Cosine theta plus your, sorry, minus, because then the plus and the minus becomes the negative. And that equals 2. The negative sign there. I got negative 0.32. 315 meters. Right, and that makes sense. You have your x in a positive direction here, and then you have your y, which is negative, as your resultant vector, so that makes sense. Then from there, we can draw your resultant vector. Got here. Resultant of a minus b. Now we know what these y and x's values are, so one goes here, y. It's negative as expected. This one goes here. Okay. So then to find a resultant vector, we have to use this. I have to use the Pythagorean theorem. A squared plus b squared equals c squared. C squared is your r. So this is probably like y squared plus x squared equals r squared. And then you square root both sides. So let's go ahead and plug that in. And draw this parenthetically. Y is negative 0.5. Sorry, 1 second. Okay, back to this. I'll leave space for the squared. And then we have x. Leaving space for the squared, and I'll just draw this in. And then you guys know how to plug that in. With that, you get 0.3. I got 8.24 meters. So then that's your resultant vector. And then that's its magnitude. Because I could draw this a bit higher. And then we need its direction, which is its theta. Or we'll just do angle. I know these things always look tedious. Notice that here you can pick whichever angle. I'm usually gonna go ahead and pick like this one. And this is your opposite. This is your adjacent, tangent. Let's go to opposite over adjacent. So we have tangent. I'm gonna do alpha. Equals opposite over adjacent, which is equal to your y over your x. And then arctangent or tangent -1 or antitangent. They're all the same thing. Or y over x is equal to your angle. I'm just using alpha. Usually use Greek letters for your angles, just so you know. Like this is the Greek letter psi theta, this is the Greek letter psi, this is the Greek letter alpha. Stuff like that. So then you have you do want to include the negative here because it's gonna affect your angle, I believe. You could write the units just to show that you know they're there, but they're gonna cancel out anyway, so they don't really matter. By the way, if your units ever don't cancel out in like one of these things, first off, that's usually a problem. But if it's like, no, I'm sure I did everything right, just make sure that they're the SI units, like the units that you're supposed to be using. Because if not, then you'll like get a different answer. For example, like if you were doing molarity concentrations or something, you would use moles. And I guess you do use them positive there. Well, it's the same thing. It says negative 2.19. It's just that's the number, I believe. And that should be all for this problem. Oh, why have we learned about vectors? Because they are useful in physics. They have magnitude and a direction, and they explain some examples are like velocity, acceleration, force. All right. This statement, vectors have magnitude and direction. If she ever asks about vectors, always add this. That's like one of the main things she wants you to understand. Because there's like vector versus scalar. So scalar doesn't have like a direction, but it has magnitude. It's just I'm gonna go ahead and clear my drawings. And then I believe the last one is this car driving on the freeway. Car driving on the freeway, it's going constant speed for 30 seconds, and then the car speeds up to that speed in 4 seconds. So you can split this up into parts. So this kilometers for 3 seconds is part 1. And this is part 2. So we'll do part 1 over here. And overall, it doesn't go down anymore. So the car is driving on the freeway. So the car through. It's 30 seconds. And the velocity vector is that way. Oh, we're assuming all on the x. 60. Notice that you have hours and you have seconds, so you are going to need to change the kilometers to hours, seconds stuff. So I'm actually going to erase that part. So we can do the conversions. Yeah. This applies for both of them. So we have kilometers per hour. You know that an hour is equal to 60 seconds, 60 minutes. So the same as 1 minute, 60 seconds. And then 1 kilometer, I need to move this down. Put it down here. I want to say 3 zeros. So 1, 2. And you know that because we have a King Henry died by drinking. That's as far as we need to go. This is your base unit, your meters. It takes 1, 2, 3 hops to get to meters. So then you have 3 zeros. With that, you convert them over. GR has them converted here. And that's also what I got. So this is 16.7 meters per second. Little 1 for part 1. And then after part 1, you're going to switch into part 2. For this section, you have 4 seconds. And your X is an unknown. I guess we should probably write 2's here. And the 1's on the other side. Note that for part 2, you have your V naught is equal to the 16. But then you have a final velocity, which is given to you here as kilometers per hour, but then you convert using this kilometers to like meters and hours, seconds conversion. And that's going to give you about 19.4. Second. And you know that because you're changing, that means you had an acceleration. So for part 1, you could do this 2 ways. You could use your X is equal to X naught plus V naught T plus 1 over 2 AT squared. And then note that these two become 0. So then your X is equal to T. Right? Or you could also do V is equal to delta T over delta T. Sorry, delta X over delta T. Which means that BT is equal to X minus X naught. This X naught becomes 0. Either way, you get X is equal to BT, which is equal to 16.7 meters per second times 30 seconds. So that means that X is equal to, I got 501 meters. So then we can go ahead and insert that here. 501 meters. And then we can do part 2. So that's for the distance traveled in that time frame. So either way, you're gonna have to find acceleration, right? So all the kinematics equations that we have use acceleration. But the good thing is you can find acceleration. You have V is equal to V naught plus AT. Real simple. You can move this over. Note that you could also, or acceleration is equal to delta V over delta T, which is probably a lot faster in this case because it's the previous form of this kinematics equation. So then acceleration is equal to I'm gonna type this out. B final should be 19.4 meters per second. The initial should be 16.7 meters per second. And then you're going to do all of that. I'll plug it in later. Over T. And that's going to give you, what did I get? 0.675. And I'll write in the units later. Over 4 seconds in meters per second squared. And then from there, she uses this one. That's probably the best one to use. You could also use this one using the X naught and your V naught, but this one's probably easiest. So then we use the V squared. Actually, no, they'll probably be about the same in difficulty. The only pro side of this one is having this delta X. So I'll do an alternative version. So that way you get the delta X there. So I'll do it this way. So you see delta X. V naught is what? Oh, let me type it. 16.7 meters per second times 4 seconds plus acceleration 0.675 over 2 times 4 seconds to the power of 2 squared. So then your delta X is equal to I got 71 meters. Feel like I rounded that. Squared. Okay, I got 72 meters. 72.2 meters. Which is about the same as this one. I guess this one's a little more accurate since you already have your V squared in there. But either way, it's about 71 and then you add them together. So it's about 72 meters. So then your X total, oops, ignore that little. Total is equal to x1 plus x2. Here x equal to 501 meters plus 72-ish meters, which equals 573-ish meters. I'm guessing we rounded a little differently. That's why it's a little different. Okay. And that's it for this exam one. I do plan on trying to record something for like practice problems later on. But I'm kind of had a headache for the last few days, so I don't know. I'm not sure if you noticed I sighed a lot here. My brain was like, eh. Anyway, hope you have a nice mid-semester break and good luck. Stop.